Hi folks, we're going to take a look at 19A from page 558. So here they're asking us to find a vector equation for the plane given by this equation, which of course is in Cartesian form. All right, so to find the vector equation of a line, we need a point. So that's easy to find. Just pick any two of these variables and then solve for the third. And we need two direction vectors. Now, the easiest way to come up with direction vectors is actually to come up with more points, because we know if we find 3 points, we can then create direction vectors using those 3 points. All right. Now, ideally, if I can find points that are nice, that don't involve fractions, that's all the better. In particular, the easiest points to find are the intercepts, because if I want to find the x-intercept, I just make y and z equal to 0, and similarly for the other two. Now, I notice here that's going to work really nicely, because look at this constant term, 6, and here I see 1, 2, and 3. So that means we can solve for the intercepts very easily. All right, so the first thing I'm going to do is look for the x-intercept, and of course that's just by letting y and z be equal to 0, so we have 3x equals, and bring the 6 to the other side, so 6, so x is equal to 2. So point 1 is 2, 0, 0. Okay, and then I'm going to do the same thing with y and z. Let me find the y-intercept. Let's make x and z equal to 0. So I have negative 2y is equal to, again, bring the 6 to the other side, so y is equal to negative 3. So my second point is going to be 0, negative 3, 0. And then lastly, my z-intercept, easiest one of them all, because if I make x and y equal to 0, I just have that z is equal to 6. So my third point is 0, 0, 6. Okay, so I can use any one of these 3 points as the point that I need for the direction vectors. All right, and if I want now, any point that I need for my vector equation, and now let's find my direction vectors. So my direction vectors can be found by just finding vectors between these points in any order. Okay, so here I think what I'm going to do is I'm actually going to go this minus that, because I'd like to keep, might as well keep positive numbers if I can. So here I've got 2 minus 0, because remember, the vector joining these 2 points is made up of the subtracting the individual components. So 2 minus 0 is 2. Here's 0 minus negative 3. 0 plus 3 is 3. And then 0 minus 0 is 0. Okay, and then the second one here, and oh, sorry, that should be vector b equals, okay. And here it doesn't matter what I use. I'll use here, I'll do this minus that. Okay, 0 minus 0 is 0. 0 minus negative 3 is 3. And 6 minus 0 is 6. Okay, now recall that if you were to do, say, them in a different order or choose different pairings, your direction vectors might be different. But that's okay, because remember I said we're looking for a vector equation of the plane. So you might come up with one that looks different than the others, but it still represents the same plane. All right, so now I have my point. So I'll pick, say, 2, 0, 0, but I could have used any one of these 3 points, plus my first parameter times my first direction vector, which is 2, 3, 0, plus another different parameter times my other direction vector, 0, 3, 6. By the way, here, any vector in this direction would work. So I could have even used 0, 1, 2. Okay, something parallel to this one. So again, this whole idea that there's many different looks to these vector equations. And here it is important, you have to specify that in order to get all the points on the plane, you need to allow s and t to take on any real value. So you have to specify that s and t can be any real numbers. All right, so just to quickly recap here, Cartesian equation to vector equation, the idea is to find 3 points on the plane. The easiest ones to find are the 3 intercepts. And then from there, once you have those 3 points, you can create vectors joining any pairings of these points. That'll create your 2 direction vectors. And then along with any one of these points, you can write out the vector equation. All right, that's it for this one.